Hello, everyone. So I hope everyone can hear me properly. So welcome to day 2 of tutorials. And my name is Mahia Shirvani Muqaddam. I am chairing this session on behalf of the organizing committee of the 2021 ISIT. So we have two great speakers today, Bulat Bash and Matthew Block. I will shortly introduce these two great speakers. The tutorial will be on the introduction to the information theory of covert communication. Bulat Bash received the AB degree in economics from Dartmouth College in 2001 and MS degree and PhD degree in computer science from the University of Massachusetts Amherst in 2008 and 2015, respectively. He is currently an assistant professor with the ECE department at the University of Arizona. He was previously a scientist with the Quantum Information Processing Group in Cambridge. His research interests include security, privacy, communication, signal processing, and information theory. He won an honorable mention at the 2015 NSA Best Scientific Cybersecurity Paper Competition, the Raytheon Space and Airborne System Excellence in Engineering and Technology Award, and the NSF Carrier Award. The second speaker is Professor Matthew Block. Is from the School of Electrical and Computer Engineering at Georgia Tech. He received the engineering degree from SUPELEC, the MS degree in electrical engineering from the Georgia Institute of Technology in 2003, and PhD degree in engineering science from the University du Franche-Comté, France in 2006, and a PhD degree in electrical engineering from the Georgia Institute of Technology. In 2008 to 2009, he was a postdoc research associate at the University of Notre Dame. And since 2009, Dr. Block has been on the faculty of the School of ECE. His research interests are in the area of information theory, error control coding, wireless communication, and cryptography. Dr. Block was an associate editor for the IEEE transaction on IT from 2016 to 2019. And he has been an associate editor for the IEEE transaction and information theory, information forensic, I lost that, and security since 2019. He has been on the board of governance of the IEEE Information Theory Society since 2016 and currently serves as the second vice president. He is the co-recipient of the IEEE Communication Society and IEEE Information Theory Society 2011 Joint Paper Award and the co-author of the textbook Physical Layer Security from Information Theory to Security Engineering, published by Cambridge University Press. So without further ado, I will now stop sharing my screen and pass over to the great speakers. If you have any question during the presentation, so please put that in the chat box. So the others, if you want to answer them during your presentation, feel free. Otherwise, I will try to answer them, ask them after your presentation. So now floor is yours. Thank you.
Thank you. Yes, thank you for the very generous introduction. Let me share my screen. And hello, everybody. Thank you for attending the tutorial. With regards to questions, what me and Matthew have decided to do is, if you have questions, type them into the chat, and one of us, whoever is not speaking, will try to answer them in chat. And then the ones that are very interesting, that would be of benefit benefit to discuss, we'll discuss at the end of the tutorial. So that's the plan. Again, this is a tutorial on the information theory of covert communication, and I am Bulat Bash. My colleague Matthew Block will present shortly. I will begin by introducing the subject of covert communication. So first, let me get rid of the Zoom here. First, covert communication is a security modality which prevents the adversary from detecting the message carrying transmission. So the transmission that is transmitted by the legitimate party has to be indistinguishable from the noise on adversary's channel from this transmitter. This is in contrast to more standard secrecy modality, which protects the message from being accessed by the adversary. So here we want to protect the message from being detected in the first place. This problem has a very rich history in both electrical communications as well as related fields. The one example that I tell everybody is the spectrum, which was invented to carry out covert communication between a US Navy ship and its torpedo, and was invented by Hedy Lamarr and George Antheil, and patented in 1942. We'll be talking about the fundamental limits to this spectrum. So it's the idea has been in this electronics engineering for quite a while, and in general, the idea of hiding transmission has been around since ancient times. In fact, steganography, which is related to covert communication, in that both try to hide data, was first mentioned in Herodotus in 440 BC in the context of Peloponnesian wars between Greeks and Persians. So let's talk about why is covert communication important. And it's important because a lot of times the adversary doesn't care about the content of the transmission. What they care about is the metadata that the transmission exists. And this was illustrated, now it's been about 8 years, but it was shock when these news came out. Edward Snowden is on the picture on the right-hand side, that this is what various government agencies care about. The other is for if you live in a under an oppressive regime, if you're trying to organize social unrest, government may shut down any transmissions, and this has happened. For example, Hong Kong or other recent protests. And the encrypted communications are especially vulnerable to this. They stand out like a sore thumb. Finally, and very importantly, military is always interested in hiding its activity, including the location of their transmitters, which is why covert comms is so interesting to that community as well. But why would be interesting to information theorists? Well, first of all, it's a zero capacity channel, zero sharing capacity channel. So it's that makes it automatically very exciting. But also the very, I would say, cool mathematical proof techniques that yield the fundamental limits of practical systems such as spread spectrum that I have mentioned, which we'll go over in this tutorial, which are interesting to learn in its own right. Finally, applications and methods from the emerging fields, including quantum information theory, are always exciting to be applied to anything. We're gonna go into those in part 3 of the tutorial. So the objectives is what we're trying. There's no way we can cover the whole landscape of the information theory, and there's another related aspect of doing the communications theory analysis of these systems, which we unfortunately won't even be able to touch because we won't be able to do justice to it. So what we're going to be focusing on is understanding of the information theoretic covered communication models, contrasting and comparing them to the other security modalities for communication. We will go over some key mathematical techniques for deriving the results so that you're exposed to them, and we'll overview the emerging areas in information theory of communication. So the structure will look like this. This is part one. I will introduce something right now, the Covert comms and related information theory results, and go over the connections to other fields. Then my colleague Matthew Block will derive the covered capacity and coding theorems for covertness, or at least give a good understanding so that you can derive them yourself. And finally, in part three, I will talk about channel dynamics and quantum information processing aspects of covert comms. So without further ado, let's jump to notation, because it's we're information theorists here and we'd like to establish some ground rules for symbols we use. We're going to use generic notation for sets and collections. For consecutive integers, we'll denote them with this double bracket, which is depicted on the slide what it means. Variables, random variables, are going to be denoted by capital letters. Their realizations are going to be small letters as a standard in probability theory. Vectors are going to be either bold or subscripted by the number of items in a vector for both random variables and their realizations. And we're going to use a standard notation for the expectational function. The probability distributions will be denoted by P, Q, or sometimes something else. Conditional probabilities will have will indicate which is the output random variable, which is the conditioned random variable, conditioned and conditional variable, sorry. And an important thing to note, especially for the second part of this talk, is the definition for absolute continuity of distribution P with respect to Q. It is simple in that it means that if a Q event has zero probability in Q, that also has zero probability in P. That's the definition of absolute continuity. I hope I got that right. I should have said this in the beginning of my talk. We have uploaded a deck of slides for just the slides we're going to present today, but we will upload a longer deck with the references included in the next couple of days or so. So I hope that if somebody doesn't have access to the slides on conference website, please speak up in chat, and Matthew will figure out how to get them to you with the conference organizer, of course. So let me continue with this presentation. Information theoretic quantities, very standard entropy definition, mutual information. I want to remind you what the K divergence is, and the total variation distance is maybe slightly new to you, but it's essentially a L1 norm between two probability densities, as defined as on the slide. We'll make use of those quantities in our bounds. And finally, I will make heavy use of asymptotic notation. And I just want to remind everybody that big O is a tight upper bound asymptotically. Loose upper bound is little o, and loose lower bound is omega. So those will be the quantities that we use, and we'll define notation as we go along in the presentation. So the first paper at SAT, arguably the first paper at SAT on covert communications was in 2012, and that's the model that it used. It's the AWGN channel model, and I feel it's good to introduce it here because it's simple and informative at the same time. And we'll expand on it in part 2 as well as part 3. So what do we have? We have our legitimate communication parties, Alice and Bob. This is Alice and this is Bob. Alice's job is to transmit a message, if she has one, to Bob without being detected by the adversary, whom we call Willie. Now, the message is she has MN of them, and they're numbered 1 through MN, and they're selected uniformly at random. If Alice is transmitting, this is denoted by a switch phi, which controls transmission state. If she is not transmitting, then she's transmitting 0 effectively throughout her block of N symbols. This transmission 0 induces noise at Bob and Willie, and the noise is independent and identically distributed for each party, each receiving party, and it's 0 mean, and the variances that are indicated on the slide, sigma squared B and sigma squared W. Alice and Bob also have a resource that they share before communication starts. They cannot use it, they can't communicate directly through the resource, but they can use it to communicate over this channel. Think of it as Alice meeting with Bob before she goes off to on her mission, if Alice is in the military, and before that they exchange secret keys. So this is what this S indicates, a pre-shared secret. And we assume that the warden, the adversary, has access to all the details of how the system is constructed for both Alice and Bob, as well as how the secret is generated, but not to the secret itself. It's very important. So the security of the system will depend only on the secret that Alice and Bob have exchanged, as well as in the inherent randomness of the channels that the information is being transmitted on. It's very important to make sure that this is not security to obscurity. So the question that we would like to ask is, what is the maximum number of bits, which is log of the number of messages that are possible to transmit, that Alice can transmit to Bob without being detected by the Willie the warden? And for those of you more familiar with secrecy literature, we usually use Willie for the adversary in covert communications. It came from steganography, this designation, and it's because the Willie's objective is fundamentally different than from the eavesdropper's objective, who is trying to learn about the message being transmitted. We'll go into that in a couple minutes. So the first question is, what's the number of bits that Alice can transmit reliably to Bob? Second is, what kind of resources are required for this to take place? And we will find bounds on both for this channel as well as other channels as well in this tutorial. So before we get started though, I will have to define some terms. And reliability being important is what we're trying to do is use usual, well, we're going to use usual definition of it. Alice is going to transmit to Bob. Bob has to decode the message with expected probability of error less than some arbitrary epsilon that Alice and Bob pick, given that the block length is large enough. So that's going to be the definition of the decoding error probability. And that's how we're going to measure reliability of a channel. So if we can meet this criterion, then we consider communication reliable. Covertness. Well, as I mentioned before, Willie's objective is to detect whether Alice is transmitted. There's only two states that he cares about, either Alice is transmitting or not transmitting. This corresponds to a binary hypothesis test that I will talk about shortly in more detail. But hypothesis H0 is absence of communication, and we assume that in that case, the readings that Willie obtains are going to be distributed with this distribution Q0, and it's going to be a product over n channel users, so it's going to be Q0 tensor product n. When communication occurs, we're going to use notation Q hat, and that's going to be distribution over n users of the channel, and it's going to be different from Q0 because we're going to make an assumption that's going to make a problem not trivially soluble, in that not transmission, there's no way to transmit something that looks like no transmission at the adversary. So Q hat is always going to be different from Q naught. But what we can do is control how different it is. And but before we do that, let's discuss the model. Let me just move this. What's going on in my Zoom here? There we go. So we're going to discuss the model a little bit more. So let's suppose that the secret that Alice and Bob pre-share before they go and go off and try to communicate is a standard random Gaussian codebook with average power per symbol PA. So this means that given that the message is selected randomly, uniformly random, the output is going to be governed by this random variable, which is a product of n normally distributed random variables correspond to the construction of the codebook. And this is, of course, if you don't know what the codebook is, if you marginalize the codebook itself. So this is how it's actually going to look to Willie, because he won't have access to the codebook. In addition, it's going to go through this channel, and the variances of the code and the channel noise itself are going to add up. And the distribution when Alice is transmitting to Willie is going to look like tensor product of normals, zero mean, and variance PA plus sigma W squared. So then Willie must perform the following hypothesis testing task for this particular codebook construction and this particular channel model. He has to distinguish n copies of a observation of a random variable that comes IID from this normal distribution versus this normal distribution. And one can actually write down a hypothesis test that the likelihood ratio test to do this, but we're not gonna do that here quite yet. What we're gonna do is we're going to dive a little bit deeper into the hypothesis testing. Our objective is going to be determine what value of power per symbol Alice and Bob can set so as to prevent the two hypotheses here from being distinguished. And going back to the original objective of the system, covert communications tries to hide the presence of transmissions in the channel noise to the adversary. So if adversary, when he looks at his channel, sees almost the same channel, it's very difficult for him to tell whether Alice is transmitted or not. And that's the whole point. So we're going to try to figure out what power Alice can transmit at so that the hypotheses are virtually indistinguishable. And to do that, we're going to look at the hypothesis test, and which will allow us to then determine what is the maximum number of bits that can be transmitted using this power. So let's look at the hypothesis test. This is a binary hypothesis test that Willy has to perform. It can be completely characterized using this particular matrix. We have 4 outcomes that are possible from this test, and it's they're classified by what kind of action Alice takes, whether she's quietly transmitting, and what kind of decision Willy makes. We care about Willy making errors. So just like in many other hypotheses and problems, we're going to assume that Willy cares both about making false alarms as well as misdetections. If Willy doesn't care about raising false alarms, he'll simply just declare Alice transmission all the time and let whoever has to deal with Alice deal with Alice. But we're going to assume that Willy actually cares about making sure his false alarm rate is low. Misdetection is obvious, and that if Willy misses Alice, he failed at his task. So we have a we also want to indicate the probability of correct detection, and we indicate these probabilities by PFA, PD, and PMD. So this is what we use. Now let's assume that Willy assigns a prior on Alice's transmission state. And we're going to dispense with this assumption in part 2. But for now, let's for illustration and so that we deal with probabilities that we're familiar with, let's assume that Willy assigns a prior. Let's assume that he assigns an equal prior. So 1/2 she's transmitting, 1/2 she's not. That is equivalent to the this is what's called the uninformative prior. And again, we can relax all this, and we will do that later. But if we assign a prior to each hypothesis being true, we can actually write down probability of error. And it's that. It's the probability of misdetection times the probability of being in hypothesis 1, hypothesis 1, plus the probability of false alarm times the probability of being hypothesis 0. So each probability is going to be 1/2, and that's the probability of error to get. Now, suppose in these circumstances, Willy simply discards all his observations, flips a random coin, and makes a choice between declaring Alice transmitting or not transmitting based on the outcomes. Well, it should be fairly easy to do the calculation and find out that the probability of error in that case is always going to be 1/2. He's going to be half right and half wrong every time. And that corresponds to a situation where if you take Willy's receiver operating characteristic curve, it's going here, his detector is going to be on this line of no discrimination. And so what do Alice and Bob do? Well, what they're trying to do is to make sure that the detector is confined. Any detector that Willy builds is confined within this line. And what they attempt to do is make sure that they pick some small delta, which is greater than 0, and build their system so that for any detector, probability of error is larger than 1/2 minus delta divided by 2. So that's what we have. And now what we're gonna look at is the impact of this requirement on the number of reliably transmissible bits log of mn. And I think that I will okay, so this is the central result. This is the square root law that was first presented at SAT 2012, and it states that the power per symbol that Alice can use such that the covertness constraint, this constraint right here, is maintained, has to be some constant divided by the square root of the number of channel users in the block that Alice transmits. This assumes that Willie knows when the block begins and ends, that he knows how the codebook was constructed but doesn't know the codebook itself. He knows what the channel noise profile is, Gaussian with zero mean and sigma w squared power, and also knows that what POA is. Given all that, which is a lot of knowledge, Alice can still transmit at this power. And the number of bits that she can get through is going to be proportional to the square root of n times the square root of delta, in the delta being the covariance criterion that we discussed earlier, plus some small terms. So this means that the channel capacity of covert channel is 0. If you go ahead and do a standard limit, you're gonna arrive to 0. But scheme exists that allows our transmission of this number of bits, which is proportional to square root of n. Unlike in standard scenario where we have the number of bits proportional to n for over n channel uses. And we call C covert the core capacity. This quantity only depends on the channel and not on the block length or delta. And to achieve it, in the SAT 2012 work, we use order of square root of n log of n pre-shared secret bits, which is larger than the number of bits that we actually will transmit. And we've argued that in many situations, including military use cases, it's actually a lot more important to not be detected than to carry an additional SD card with key. But that being said, in part 2, we will show improvement to all square root of n for the number of pre-shared secret bits required, as well as condition when it is 0. So let me now go, and before I go and prove the results, I don't think we're actually going to have time to prove these results because I will try to get to part 2, which I think is quite a bit more interesting. But let me contrast what covert communication is with steganography as well as other security modalities. So steganography, you may have seen it in the context of covert communications. It's where an image or text or some other, usually digital object, get changed using an embedding procedure and transmitted by losslessly. Let's assume that the transmission is lossless to the receiver, who extracts the information that was embedded. And the idea is to embed it in such a way that a powerful adversary cannot detect the presence of this embedding in the transmission. So think of change in the least significant bits of an image to put in another image. It's actually a very poor steganography scheme, but it was used. In fact, I believe that there was a news article written about an FBI investigation that was into a criminal organization was using that to do their communications. But that aside, the way it's modeled information theoretically is that there is some cover text source, which is governed by the probability distribution PU, and this might be a distribution over all n symbols, cover text symbols in the cover text. There is some pre-shared secret key between Alice and Bob, and Alice again choose between embedding or not embedding. I will not go too deeply about into the steganography results. We don't have time for that. I will point out the difference, the main difference is that steganography allows one to essentially manipulate the cover text and the inherent randomness of it. And this is not what covert comms does. Covert comms cannot, the randomness that is exploited in covert comms is the randomness of the channel. And we have no access to that. It's as if we managed to get into Willy's detector and change the random fluctuations of electrical currents that occur in his electronic components. We cannot do that. If we could, Willy has much bigger problems than Alice transmitting covert data to Bob. So steganography by its design allows one to do this. And thus the laws for it are different. The scaling law is not square root, it's linear if you assume Markov cover text. And this is a result by Boris and Daniil Repko, their brothers, and was published in 2011 in a information computation, I think is the conference name. This motivates the fact that if you have a characterization of a cover text, it motivates approaches that seek this characterization and exploit it for embedding. And this was the main drive between for work, early work by Phil Sully, as well as this model-based description of steganography present in Christian Kachan's work. And Pierre Moulin and his group have also done a lot more to extend it. They took a different approach, a ray distortion theory approach, and actually quite a common trend is to also assume that the adversary is changed in the cover text after the embedding happened. So a change in second text. So there is some noise that comes in afterwards and it's accounted for in some of these works. So a good textbook that talks at length about both the practical as well as information theoretic aspects is Jessica Friedrich's book that was published in Cambridge University Press in 2009. And I will also say that the root laws, like the one we described, have been known to steganographic community since at least 2005. There was work by Valery Kozhak at the International Watermark and Digital Media, now international. I forget what the abbreviation of the conference. It had to do with watermarking. It's a conference, and what he examined is the model where adversary corrupts the stegotext with AWGN. The difference between that work and ours is that even though one could derive the achievability result from it, there was no converse in it. And Andrew Carr has had a lot of papers on the square root law for digital steganography. Arguably, one could say that Brother Repko's work on linear law superseded those. So, but stenographers have made quite a lot of progress on square root laws. That's for sure. So that's all I'm going to say about steganography. Let me now talk about information theory secrecy. And this is a standard model where you have Alice and Bob and Eve, and Alice wants to transmit message to Bob via a noisy channel. Eve has her own noisy channel to Alice, and she wants to extract information about the message from transmission. Notice that there is no notion of innocent transmission here because there doesn't need to be. Eve doesn't care whether Alice transmits or not. She only cares about what she transmits. And the main result is going back to Weiner's 1975 work and other works that followed, is linear law. So there is a capacity, and that's the formula for it, where the maximization takes place of an auxiliary random variable v, and then the capacity is the maximum difference on information received at Bob and eavesdropper about the auxiliary random variable. The main thing I'd like to highlight is that secrecy is a constraint on the information that's contained in signals, while covertness is a constraint on the structure of signals themselves. So this we're going to be talking about structure more so than information content, but both are important. It's just covertness emphasizes one of them much more strongly than secrecy does. And I would like to also point out the condition for positive secrecy capacity, meaning that the channel from Alice to Bob has to be better than the channel from Alice to Eve, resembles the condition over which the condition for necessity of a pre-shared secret in covert communications, which we'll go over in part 2A of this tutorial. And that condition in covert comms terms is that the channel from Alice to Bob is able to distinguish the non-innocent transmission from innocent transmission better than the channel from Alice to Warden. So there are lots of similarities, and some techniques are borrowed from one to the other. So we'll try to go through that. So the place where covertness and secrecy get combined is what was called effective secrecy by Gerhard Kramer and his student Jihu back in 2014. So the covertness effective secrecy is where you have your scenario from covert communications, except that Willie allows positive entropy analysis transmissions and also cares about the content of the message that Alice transmits. And we're missing on this figure a extract of information about a message in this particular Willie's box, but think of it as being there. So the two requirements are stealth, which means that Alice must transmit from the distribution that was given to her by Willie. And notice, not the instance of a distribution, but the distribution. So Alice can actually transmit as positive entropy. She's allowed to. And the instance distribution is defined as marginalization over this distribution from which she has to transmit. And the other result is a secrecy result, in that she has to prevent the adversary from accessing the message. And what we want to control is this particular measure, which is the KL divergence or relative entropy, which can be decomposed into two components, each corresponding to secrecy and stealth. And I will not go too deeply into the derivation. It is very interesting. I encourage folks to look at these papers. But the main result is that this, as one would expect, given that positive entropy transmissions are allowed, you have all n bits reliably transmissible under these requirements. And innocent transmission, X0 under the null hypothesis, is essentially a degenerate version of QLX. But even though it is degenerate, the result that we have is quite interesting in its own right, because we don't go to zero, we go to square root 1. So this is interesting. And I have to point out that in the SIT 2020 paper from last year, they characterized the region between covertness and this O of N law. So, and finally, one cares about ensuring both covertness and secrecy simultaneously. But we can also say, from looking at this work, that one can be secret but not covert, or be covert but not secret. Secret but not covert is very obvious. Covert but not secret means that if the adversary assumes that the transmission is there, that they have the correct decoding of it. So it's an interesting, interesting line of thought. So, and finally, I want to make a connection to the space spectrum, which is what motivated my study of this um, back in 2011. Um, and this illustrates the direct sequence space spectrum. We have a narrow band signal that you spread over wide band by multiplying it using a spreading sequence, and thus the spread signal falls underneath the noise floor. Well, the question from this system is what essentially the purpose of the system spreading over a large frequency band is what Hedy Lamarr and George and Thiel invented back in 1941. The question is, what is the noise floor? What is the power that is safe for the transmitted signal to not be detected? And it turns out that given the if the noise floor is constant, it's the screwed line, it's kind of a screwed line that we derive. So it's I feel it's kind of interesting that from 1940s to 2010s, folks didn't quite think about this in terms of information theory, at least of what we know, and it was kind of cool to make this connection. So, as I said, it allows one to quantify the safe power level. We also can quantify the resources, the secret that we need to exchange prior transmission in order for this to succeed. And furthermore, the amount of information is being transmitted. So we're going to look at the encoding schemes for it. So we're going to focus part 1 and part 2 of this tutorial on the static channels, which resemble noise flow not moving. But in part 3, I'm going to talk about what happens when noise flow moves. So I think I will skip this slide because we are already running ahead of time. But this basically tells you how to lower bound Willie's probability of error for achievability using information quantities. We can go back to this after the tutorial, but I will skip it for now. And the main thing to note here is that we use fairly standard techniques to get our lower bound on probability of error, and then employ maximal decoder to obtain the reliability. So I will very briefly go into the converse that for SRO. The converse, basically what you do is you assume that Willie, you give Willie a device, radiometer. You have a radiometer basically collects the squared readings of the channel, and you test them against the threshold. In this case, the threshold is the noise that he expects to see plus some tau, which he has to have. And he accuses Alice if the average power exceeds the threshold, and doesn't accuse her if it doesn't. So the power is distributed as chi-square distribution, and so we're gonna plot this and graphically illustrate what happens in under hypothesis H0 and hypothesis H1 when when Alice does not transmit. The mean of Willie's radiometer readings is going to be sigma W squared. It's the noise that he experiences. So whenever the test statistic S exceeds this mean plus the threshold, he's gonna make a mistake and accuse Alice, and thus waste resources. When Alice is not transmitting, we can use the Chebyshev inequality to bound the probability of false alarm and determine that the threshold decays as 1 over square root of n. You can see the square root of n right here. When Alice is transmitted, the mean is going to be sigma w squared plus the power of her transmission. So, and here, by the way, we assume that there is arbitrary code that Alice is transmitting some symbols which we don't know about. We don't give any information to Willy on the structure of the code, on whether it's a Gaussian or not. It's an arbitrary string of symbols. But you can calculate the power by just squaring and taking average. So that's the power. It turns out, understandably so, that when the power is increasing greater than 1 over square root of n, then these the misdetection probability goes to 0. And it's very easy to see from the plots. The mean of the distribution when Alice is transmitted is going to be sigma w squared plus pa. The threshold is going to be set to something which is 1 over square root of n. So if POA increases or doesn't decrease as 1 over square root of n, the two distributions are going to separate between each other, and you're going to have very small probability of misdetection because this is staying in the same place, relatively speaking. So that's the graphical illustration of this process. And what this means is that any code word with average symbol power, POA significantly greater than 1 over square root of n, is detectable using this very simple geometry. And this intuition was given in an article I wrote for the IEEE Communication magazine in 2015. It's somewhat dated, but I feel a nice introduction to the information theory of covert communications. Very briefly, how do you show that beating this detector doesn't result in exceeding the square root law? Well, in order to beat it, you have to designate some constant fraction of the codebook, and again, it's an arbitrary codebook, whereas so with power decays is 1 over square root of n. And this doesn't allow Willy to try detection probability to 0. So we can then do some lower bounding on the probability of error for Bob by a simple law of total probability. And this is the fraction, and this is the probability of error for this fraction. And we're going to calculate the probability of error for this fraction since we're trying to send greater than square root of n bits in channel uses. With this power, we can adapt the converse to Schoen-Cohen theorem to show that the probability of error is always going to be greater than 0. And thus, the decoding probability overall is also going to be greater than 0, and we cannot meet the reliability threshold. So the bad news about this approach is that it results, well, the good news, the bad news is that the argument yields a nice square root scaling, but it doesn't give a good bound for code capacity. It also does the good analysis of Schreiber size. As I mentioned, it's going to be for the particular code book that I've presented. It's going to be on the order of square root of n times log of n. The good news is that Matthew is going to present multi-technical arguments next and allow characterization of the Covert capacity as well as Schreiber size. Before I end my part of the talk, I will just want to point out that the covert communication and related disciplines have been known by many names. And on this table, I tried to summarize the characteristics as well as the names. And you can see that for covert communication, there was a number of different names for that the researchers came up with. So if you're a student, if you're looking to find out what was written on the topic, you should search for all of this. So with that, I conclude part 1 of the talk, and we'll pass it over to Matthew. Sorry for running a bit over.
No worries. Hey, everyone. So my part is actually 2 very natural sections. So I'm planning to have a little break once I go over the first part of my talk. And without undue delays, let me share my screen. All right, Bulat, can you confirm that you see my screen?
I can see your screen, yes. I'm going to mute myself.
Excellent. All right, so as Bulat said, the goal of this new section of the tutorial here is to refine some of the characterization of covert communication that Bulat alluded to earlier. And my goals for the tutorial are really threefold. The first thing I want to do is I want to introduce the notion of covert capacity. Bulat has hinted at what it is. What I'll try to articulate is that it's a quantity that plays a very similar role to the capacity that we might remember from an information theory class for reliable communication, but it's also a quantity that has very unusual properties. And for instance, I'll argue that there is no strong converse. And if you don't know what a strong converse is, don't worry. I'll define that more precisely when I get to it. In the process, what I will also try to do is to show you how one can identify the minimum amount of resources, which in the case of covertness here are in the form of secret keys that are required to achieve the covert capacity. And as Bulat articulated, if you have few secret keys, you potentially have a more robust system from a crypto perspective. And therefore, that's important to understand how many resources you need to achieve your goal. And my focus will be mostly on discrete memoryless channels, because I think conceptually it captures the problem that we're trying to solve in a simpler way. But then I'll mention how one can hope to extend them to AWGN channels, for instance. And the trick will be to make an equivalence between power and average code word weight. My second goal for the talk will be to introduce a set of very keen technical tools that I think are central to study covertness. And specifically, I will talk about a tool that is very close to my heart that's called the approximation of channel output statistics. I'm not the one who invented it, but I've been using it a lot in the context of security, so I'll go over that quite a bit. It goes with many names, such as channel resolvability or soft covering. Yes?
There's a problem. I think the presentation isn't displaying.
Okay, so do you see my slides now?
Yes, we do.
Okay, so let me try one more thing.
Try full screen and just go in and share sharing that particular screen on Zoom.
Okay.
Thank you, folks, for pointing this out in chat.
Let me try one more thing. And then... So do you see the animation when I go now?
Yeah, that's great. Yeah.
Yes.
Okay, so I don't know what happened. Sorry about this. So what I was saying is that I will talk about this tool called approximation of channel output statistics that plays a central role for the analysis of covertness. And I'll show you how it matters both in the achievability and the converse that you need to develop to identify the covert capacity. And finally, I'll try to make a case for the importance of structure, especially in the form of sparse signaling, as an absolutely essential building block if you want to not just characterize covert capacity, but also worry about designing actual codes. And I'll give you one example of how you could actually try to design an explicit covert capacity achieving codes. All right, with all that said, let's dive into the heart of the problem. So my first part 2A is going to be about covert capacity. We'll then take a break and then we'll talk about the design of actual codes. So very briefly, just to make sure that everyone is still with me, I'm going to use the same notation Bulat introduced. There's nothing particular about it. The only one maybe is this idiosyncratic notation I have here For a set of integers, I denote them between brackets with double bars. I really just mean a sequence of consecutive integers. In terms of random variables, I'll use capital letters. Their realizations will be lowercase letters, and I'll use this capital E with a double bar as a notation for expectation. Probability distributions, I typically will denote them by P or Q, so as to not mix them with X, Y, Z, which are random variables. The one thing I want to recall you is this notion of absolute continuity, because I will talk about it just in the next slide. It's important for covert communication. And we say that P is absolutely continuous with respect to Q if the support of P is included in the support of Q. And we'll see that operationally it means something for covert communication. And finally, I'll use repeatedly information theoretic quantities, entropy H, mutual information I, and I'll use several F divergences between distributions. Bulat has already mentioned two of them in the form of Kullback-Leibler divergence and variational distance. I will also use another one of these, which is called the chi-square distribution, but I will discuss it when it shows up in the analysis. All right. So let me formally define what covert communication means in the context of a discrete memoryless channel, and we'll try to characterize the covert capacity of that channel. So we're given, as we saw before, three parties, Alice, Bob, and Willie. Alice and Bob are the legitimate terminals trying to communicate covertly. Willie is the adversary. What's happening is that Alice has a message W, which takes mn values, uniformly distributed, and it's trying to encode it, and it's allowed to use what's called a secret key that takes kn values uniformly distributed. The secret key is shared with Bob and is viewed as a resource. Okay, so we'll have to worry about how expensive it is to use the key. And so using W and S, Alice has the ability of encoding that into a code word sequence that's called X, but it also has the ability to not transmit, in which case there is a switch, which I denote by phi here, that takes two values, 0, you don't transmit, in which case Alice only sends a fixed symbol, which I called X0, into the channel. Okay, so that innocent symbol, X0, it's really required here to model the absence of communication. So that's a little bit of a specificity of DMCs, because in a DMC, you need to specify all the input symbols that you can use. They have to be a legitimate symbol in your input alphabet. That's a little bit different from, let's say, an AWGN channel where there's a natural innocent symbol, which is 0 at the input of your channel. Here, we have to be very explicit and specify it. And so when you take that fixed input symbol and you transmit it through a memoryless channel, so the memoryless channel that is characterized for Bob is the one with transition probability WY given X. By fixing the input X0, I call the output distribution P0. I remember the channel introduces noise, so even if the input is fixed, the output is a distribution, or it has emit symbol according to a distribution. I call it P0 for the channel seen by Bob. For the channel seen by the adversary, I will call it Q0. So it's equal to W, the transition probability of Z, given fixed input X0. Now, because we're interested in transmitting information, we need to introduce a new symbol. And I'm going to call that new symbol X1, which has to be different from X0. And similarly to X0, that symbol X1 at the input to the channel induces distributions P1 for Bob and Q1 for Willie. Now, I'm only going to restrict myself to channels that only have these two symbols, X0 and X1 at the input. That will simplify the analysis, but conceptually, we're not losing anything. It's going to be fairly easy to generalize to a situation where, say, you have more than one non-innocent symbol X1, and even to the continuous case like AWGN. So we're really not losing anything conceptually. We're just making our life a little bit easier in terms of exposition and niceness of the result. All right, so now to talk about covert communication, we need to be a bit careful about that channel model. We need to define a few or introduce a few assumptions that are required for the problem to make sense. So remember this notion of absolute continuity. It's actually, I'm going to require that some distribution are absolutely continuous with respect to another. So specifically, I'm going to require that P1 is absolutely continuous with respect to P0. What that really means is that when Bob sends the symbol X1, there is no way for him to generate at Bob's output a symbol that would not be able to be generated when he's sending X0 at the input. Okay, so that's a technical condition. If you want more understanding of why that's there, you'll have to read one of my papers. But let me focus on the second set of conditions, which I think are much more operational. The first condition is that Q1 is absolutely continuous with respect to Q0. What that really means, again, is that when Alice sends symbol X1, there is no way for her to generate a symbol that would not be generated by presenting the symbol X0 at the input. If that were not the case, understand that Willy, just by seeing that unique symbol that cannot be generated by X0, would know for sure when Alice sends X1. And if she sends it repeatedly with high probability, Willy will always detect Alice. So if you want covert communication to be possible, you need that assumption that Q1 is absolutely continuous with respect to Q0. The second condition that we introduce is that Q1 is not equal to Q0, meaning that there's a difference between transmitting a nothing, X0, or transmitting something, X1. If that were not the case, understand that covert communication is completely trivial because no matter what Alice transmits, Willy can never distinguish the two inputs of the channel. So these conditions, even though they're mathematical, they're actually very operational. You need to restrict a little bit the channel for covert communication to make sense. And finally, there's a code book, which is a set of all code words that can be encoded by Alice using the message W and the key S. So they're denoted collectively by X and they're indexed by 2 indices, L and K, L for the message, K for the key. And we're assuming that that code book here is known to all parties. So what is not known to all parties is the message W from the perspective of Bob and the message W and the key S from the perspective of Willy. Now, what we want to do is we want to ensure reliability, meaning that Bob is able to recover the message W and is able to understand if Alice is transmitting or not. And from the perspective of Willy, the warden, that is the adversary here, is trying to distinguish between two hypotheses. One is the hypothesis that over n channel uses, you're not transmitting, in which case the probability distribution that it expects is a product distribution of that distribution Q0 that I defined earlier. If Alice is transmitting, because Willy knows the codebook used by Alice and also knows that the message W and the key are uniformly distributed, Willy would expect a distribution that called Q at n. And that distribution has a form that is a little bit complicated, shown here on the right, but what it's really telling you is that you're observing a mixture of n-letter distribution which are induced when Alice chooses at random a code word from her codebook. Okay, so that's a mixture of non-ID distributions. So there's a lot of structure in Q at n, and what we're asking for is that we want to design the coding scheme in such a way that it's very hard to distinguish Q at n from Q0n. So that's here the challenge of covert communication. Now, let me revisit the performance metrics slightly more formally. So in terms of reliability, I'm going to use something that is not strictly speaking a probability of error, but that can be analyzed as such. I'm going to call it PE, and what it measures the probability that Bob doesn't decode W properly, given that it knows the key and given that it knows that the status of the switch that Alice is using is at 1, so that she's transmitting, and we're maximizing over all possible keys. So it's a bit of a weird average probability of error over the message, maximized over the key. The idea is that we want all keys to operate equally well. And we're going to add a term, which is the probability that Bob misunderstands what's going on and thinks that Alice is transmitting when she's not. That's going to be our reliability metric. For the covertness metric, we're going to look at several options. But the idea is the one that Bulat highlighted at the beginning of the presentation today, which is that for any test T that is conducted by Willy and applied to its observation Zn, what he's getting from the channel, so n observations coming from its channel, the probability of false alarm and misdetection of any test, they have to be bounded by the following equation. The sum probability of false alarm and misdetection is bounded by 1, and it's lower bounded by 1 minus the total variation between the two statistics that Willy is trying to distinguish, Q0n, when Alice doesn't transmit, and Q at n, that complicated mixture distribution that happens when Alice uses code words. And one can further lower bound that equation here using Pinskers inequality by 1 minus the square root of the relative entropy between Q at n and Q0n. Now, what this suggests is that if you want to achieve covertness, you want to squeeze the sum probability of false alarm and probability of misdetection very close to 1. So what you want to do is you would like to design a coding scheme that minimizes the total variation or minimizes the relative entropy, because in both cases, if you make this quantity small, you are guaranteed that you're making it impossible for Willy to detect the presence of communication. Now, if you think a bit hard, a bit more, there are actually more options than that. So what I'm illustrating here is I'm illustrating the performance of the detector used by Willy as an ROC curve that represents 1 minus the probability of misdetection as a function of the probability of false alarm. Any test in the Neiman-Person formalism where you don't put priors on the probability of transmissions or non-transmission is represented by an ROC curve, such as the one illustrated in black. As Bulat mentioned, the line in blue, which is a diagonal line between the point 0, 0, and 1, 1, is actually a completely uninformative test that you can actually generate without looking at the observation. So what we always want to do for covertness is we want to constrain the ROC curve in black to be very close to that blue diagonal line. Now, if we were to know how the adversary is operating its detector, say it's operating with a certain probability of false alarm, alpha, then what we could require is we could require that the probability of misdetection not be too large with respect to alpha, specifically of the form beta alpha, so the probability of misdetection associated to the probability of false alarm alpha should be greater than 1 minus alpha minus delta, and we want delta small. That corresponds to constraining the ROC curve for a specific probability of false alarm. But of course, you see the problem here. We can only do that if we know the probability of false alarm used by the adversary. So what total variation is trying to do when you're writing that covertness is essentially requiring that you minimize the variational distance between Q0n and Q at n, what you're trying to do is you're trying to uniformly bound the ROC curve away from the diagonal line, which corresponds to an informative test. So in particular, you can think of the criterion V less than delta to mean that you're constraining the ROC curve of any test, including the optimal one that the adversary could deploy, delta away from this non-informative diagonal test ROC curve, which when delta is small mean that they're essentially identical. But so the difference now is that we're uniformly bounding the ROC curve without requiring any knowledge of where the adversary is going to operate. And if you choose to use the relative entropy to define your covertness metric, understand that you achieve the exact same effect of uniformly bounding the ROC curve, except that because the relative entropy is only meaningful for detection as a proxy using Pinskers inequality to upper bound the variational distance, it's going to lead to a loose bounding. So potentially it means that you're going to be enforcing too much and you're going to artificially reduce your ability to be covered just because you're requiring something slightly too strong, which I'm highlighting here on that last figure. So given that discussion, which metric should we really use? So the main point I want to convey is that the metric that makes sense is the variational distance, because that is the one that is the most operationally related to the problem of detection, as illustrated by the equation above here. And the others are just proxies that you could choose to use, but they don't have the same strong operational meaning. All that said, using the relative entropy is very appealing because relative entropy is such a nice metric to use and the results tend to be simpler. And so today, I'm going to focus, unfortunately, mostly on explaining what happens in terms of relative entropy with the understanding that all the concepts I lay out will translate nicely to variational distance, but the technicalities are slightly more intricate and I didn't think that was the wisest choice for a tutorial. All right, so again, variational distance is the covertness metric that we would care about because it means you're universally bounding the ROC curve of the adversary to be close to the non-informative ROC curve, but we're going to use relative entropy, which we know is imperfect, but is going to be much easier to analyze. All right, so our goal here is to analyze the covered capacity, and we need to think a little bit to define it properly. So let me define it, and then we'll discuss what we're trying to do. So let's consider a coding scheme such that the probability of error that I defined earlier goes to 0, and the metric, whichever actually one of the three metrics I discussed before you want to use, is bounded away, from above by some small quantity delta. What we're going to try to characterize is we're going to try to characterize some numbers positive, R and RS, such that we can guarantee that if you look at the ratio of log m, the number of message bits you transmit, normalized by square root of n times a function of delta, then you're greater than R in the limit of large block length. And simultaneously, if you look at the number of key bits that you require, log of kn, normalized again by square root of n times a function of delta, it's going to be less than Rs. So we want the maximum, ideally we want to find the largest R and the minimum Rs. So we want to achieve the maximum throughput with the minimum amount of key resources. And so that's what I'm going to define as a covered capacity. So the covered capacity is a supremum over all possible coding scheme that you could try to deploy, such that they are reliable and covered in the long run. And we're interested in characterizing the ratio of log of the number of messages we transmit, so number of message bits, divided by square root of n times f delta. And for that specific amount, we're trying to find the associated minimum number of key resources that we need. So if you look at my definition of covered capacity, there's something unusual about it, right? There's a dependence on n and delta that should make you frown if you've taken an information theory course and you remember capacity. I'm normalizing by square root of n, not by n, and I'm normalizing by a function of delta that I'm not even specifying. And so if you want that weird normalization to make sense, you should make sure that at the end of the day, to call what I call C covert and SK covert capacity, you should make sure that it only depends on the channel statistics, but not on the user parameters, such as the block length n, or even the choice of the covertness parameter delta. And so what it means is that we're implicitly saying that to talk about covered capacity, we're identifying the scaling with n of the number of bits of message or keys required. So here it's square root of n based on Bula's earlier discussion, but we're also requiring that we identify the dependence on delta. Now, if you remember my somewhat cryptic comment about the absence of strong converse, it shows up here. If you remember the notion of traditional channel capacity for reliability, forget about covertness. What we know is that the capacity is the same, whether you require that the probability of error goes to 0 or the probability of error less than epsilon for some small epsilon. It doesn't change the fundamental limit. But here, what I'm claiming, without proving it yet, is that I have to normalize by a function of that coveredness parameter delta, which means I'm implicitly telling you that we have to be careful because the choice of delta and the choice of the metric used to measure delta will actually have an impact on the number of bits of messages and number of key bits required to be covered. So that's quite unusual. And ultimately, if you don't believe that definition or you think I'm wrong, the coding theorems will ultimately tell us whether that definition is correct. Because if I get the wrong scaling of the number of bits with n, say I normalize by n or n to the power 1/4, I will get a capacity that is either 0 or infinite if I don't get the right scaling with n. Furthermore, if I don't identify the right function f of delta, I will obtain a number C covered or SK covered that depends still on delta, right? So I have to identify the correct normalization, and I'm claiming this is the right approach. Now, to be a bit more specific, I'm going to give you the answers, and we'll talk about proving one of them. So if I choose for my covertness metric, the relative entropy, and that's the one we'll focus on extensively later, I'm claiming that the function of delta that matters is a square root of delta. And for that choice of f delta, together with a normalization by square root of n, and I apologize, my square root in my definition of C covered is going over f delta, that should be removed. The covered capacity is that nice expression, which is the square root of 2 divided by chi2 of q1 versus q0. So chi2 is the distance between q1 and q0. It's a very specific type of f divergence, multiplied by the relative entropy between p1 and p0. So just for a second, let's think what this is telling us. Beyond the specifics of the form, which we'll have to prove and establish together, intuitively, this makes a lot of sense because it's telling me that if it is very easy for the adversary to distinguish Q1 and Q0, meaning it's very easy to tell whether you're transmitting 1 or 0, then chi2 of Q1, Q0 is going to be very large, and you see that your covered capacity goes down. In contrast, if it's very hard, the chi2 goes up, goes down, and therefore when you divide by chi2, you see that your covered capacity goes up. Similarly, from the perspective of the legitimate receiver, if it's very easy to distinguish symbols 1 and 0, the relative entropy is large, you get more covered capacity. If not, it goes down. Now, if you change the metric and you use the variational distance, you see that the function f delta gets more complicated. It's an inverse q function, q minus 1 applied to 1 minus delta over 2. But yet again, through some analysis, you can characterize the covered capacity. And even though it has the same, somewhat similar appearance, you have to be careful. The exact expression changes a little bit because it starts depending on the specifics of the metric that you use. And finally, just to be complete, you can also analyze that weakest metric I discussed above, where we assume we know the probability of false alarm at which the eavesdropper is operating, in which case f of delta takes yet again a complicated function that depends on delta, alpha, and an inverse Q function. And yet again, you get a slightly different expression of covered capacity, even though in all cases, one could argue that the chi2 distance and the relative entropy always show up, okay? So again, you have to trust me that these results are correct. You can find the derivation in the papers that I mentioned at the bottom. But what it shows you is it shows you that the choice of the metric matters. And today we're going to spend most of our time talking about relative entropy because that's easier, even though I emphasize yet again that variational distance is really the one we should care about because that's the one that's directly operationally connected to the detection of the adversary. All right. So this is the result we'll try to establish together. What we'll try to establish is the expression for covered capacity under a relative entropy metric that I showed before, but we'll also show that associated to that covered capacity, we have a minimum amount of key, which is given by the expression given below here, square root of 2 over chi2 q1 q0 times the difference between the relative entropy between q1 and q0 minus the relative entropy between p1 and p0, and that plus operator here means that it's 0 if it gets negative. So that answers a question I got earlier in the chat today. You see that if the channel to the adversary is worse than the channel to Bob, in the sense that dq1 q0 is less than dp1 p0. That means literally that the adversary has a harder time distinguishing 1 and 0 compared to the legitimate receiver Bob. You see that that quantity here is negative, and because we take the plus, it's 0, in which case you don't need a secret key at all. But the moment the channel to the adversary gets better than the channel to the main receiver, measured in terms of dq1 q0 being greater than dp1 p0, then suddenly you start needing resources in the form of secret keys. Now, what's important is that the scaling associated is always square root of n, but this is the constant in front of that square root of n number of key bits that we need. So what's important in that result is that it's telling us that everything scaled like square root of n, and that's a critical improvement over the original scaling of square root n log n that Bulat alluded to earlier, which was suboptimal. Of course, it gave you the right intuition about the covered capacity, but it was a little bit pessimistic in terms of how many resources you needed in terms of secret keys. And if you want to start applying these ideas of coverdness together with ideas of key generation, it's very important that you don't end up spending more key resources than you can generate. So the square root of n scaling was quite central in that regard. And what we're going to show together in the rest of my section is that we can prove that result using 3 tools. I'll first define a notion of covered process, and then I'll review channel coding for reliability, and I'll introduce a notion of channel coding for approximation of output statistics, and then we'll put everything together to derive the result. All right. So let's try to derive some intuition as to what's going on here. The transmission of information requires coded modulation, right? We need to use x0 and use x1 if you want to transmit some information. But at the same time, because we want to be covered, we cannot transmit x1 too much. We have to send mostly x0. And so to resolve that tension, it's good to do a little bit of a thought exercise to understand what's going on. So I'm going to represent things heuristically on the diagram. On the left, I'm going to show modulated time signals, modulated signals in the time domain, sorry. And on the right, I'm going to show the empirical statistics that the adversary will perceive. So I'm going to assume that if you transmit x0, you will observe statistics q0 given by that bell curve. And if you send x1, this is shifted. So in principle, it's possible with a test if you have enough observation to distinguish whether x1 is used or not. And so you see that when you actually modulate data, it means the transmitted signal oscillates between 0 and 1. What you get at the output from the perspective of the adversary is a mixture of q0 and q1. So it's a distribution that in principle has 2 modes here. So the only way to be covered is to actually control the fraction of ones that we use in such a way that that bimodal distribution in dashed black here becomes indistinguishable from the distribution q0, which is the one the attacker expects when there is no communication. And so you see that intuitively, you need very few ones because you need the 2 modes that you induce because of the mixture to be nearly indistinguishable so that there's any hope of being covered. And so that reasoning will try to formalize to identify the optimal fraction of symbols x1 without worrying about coding. So we'll try to do that reasoning and that identification of the optimal fraction of x1 on uncoded data, see if we can meet the coverateness constraint, and then we'll worry about coding. And then we'll worry about making sure that the coding, which introduces redundancy across time, does not help the adversary. And that's where the approximation theory of output statistics is useful to show that even though we have coding, so that you have structure and time, this will be imperceptible from the perspective of the adversary. Okay, so we're going to try to formalize that over the next few minutes. So step one, let's try to formalize what is the optimal fraction of x1 that we need, assuming we had encoded data. So if you have encoded data, all you have to decide is the stochastic process that you use to generate your data. So I'm first going to define a parameter, alpha n, that's going to control the fraction of x1 signals I send over a sequence of length n. And because of what Bulat has already discussed, I know it has to be on the order of 1 over square root of n. Okay, so if you think about it, Bulat talked about it in terms of power. The power has to scale like 1 over n, or 1 over square root of n, I forgot already, but so here the weight of the sequences you send has to scale like 1 over square root of n, and I'm allowing, maybe a constant omega that I get to choose later. Now my uncoded data, it's going to be an ID process, and that ID process essentially at every time instant, I get to either send a 1 with probability alpha n or a 0 with probability 1 minus alpha n. If I present that process, which I call pi alpha n, so it's Bernoulli with probability alpha n, at the input of the channel to Willy, it induces a mixture, which is a mixture between Q0 with probability 1 minus alpha and Q1 with probability alpha. And the same holds for Bob at the output of his channel for probabilities P alpha n as a mixture of P0 and P1 with the same coefficient. Now, what one can establish then is the following interesting result. If you look at the relative entropy between that process Q alpha n used n times, so that's what the absorber would observe if you were to transmit that uncoded ID process n times over the channel, and you compare it to Q0n, what you expect to receive when you don't transmit. Because relative entropy is additive, it's n times d Q alpha n Q0, and it's possible to make a more precise analysis to show that it behaves like a constant, actually, omega squared over 2 times chi2 Q1 Q0 plus some smaller order terms that we can neglect. So effectively, this is telling us that the reason the square root law is there is because for that choice of fraction of encoded data symbol x1, we are guaranteed that we can control the relative entropy and it doesn't grow with n. It's actually, we have identified the scaling that makes it constant. And you can see if you want to make it such that the relative entropy itself is less than delta, you have to play with the constant omega. The second thing that you can prove is that if you look at the mutual information that's being transferred across the channel, when you use that encoded data with the fraction x1 of symbols in it. So I'm talking about information here, heuristically, there's no coding theorem yet. But if you look at the information between x and z, where x is the input and z is the output, x is distributed according to pi alpha, z is distributed according to q alpha, it behaves like alpha n times the relative entropy between q1 and q0 minus a term that actually goes to 0 much faster, so we can neglect it. And so what this is telling you that all the relative entropy terms that I highlighted in the previous theorem, they're actually mutual information terms in disguise. They show up by relative entropy because of the very specific and unique way I have of choosing the statistics of my input process. All right. So this is telling us how we should start approaching communication. First, we know now, using that lemma, that if you want to be covered, we can do that by using an ID process that has a properly chosen fraction of x1, and we know it's going to be covered because we can then, through that constant omega, control the value of the relative entropy. So now, instead of trying to focus on being covered, we know how to do that, right? So if we can somehow simulate that process Q alpha n ID, we're done. We're going to try to focus on coding so that we can approximate that process Q alpha n. But at the same time, we're going to try to make sure that we can code while IDing the structure of the code. And so we're going to use two tools from information theory, one for reliability, the other for the approximation of output statistics. All right. So the problem of channel reliability is well known in information theory. I'm going to go over it because I'm going to use it in a specific way. So forget about covertness for a second. I'm going back to your information theory lectures here. So the problem here is we have a uniformly distributed message W over 1M that we encode deterministically into a code word we call X. It takes one of M values deterministically. We're transmitting that through a noisy channel with transition probability WY given X. The receiver observes Y and tries to estimate W hat. The code C is known to all parties, and we're trying to measure reliability in terms of an average probability of error. So what we know from the 1950s now, and something that I'm going to present here using the approach that was repopularized by Polyansky, Poor, and Verdu in 2010, I'm going to give you the result information theories derive in terms of a random coding argument in a one-shot form. So what you can show is that if you want to show that you can code over such a channel, instead of trying to think really hard about how to design the encoder, you can do things randomly. Specifically, if you sample your code word randomly according to a distribution Px, which induces a distribution Py at the output, then it's possible to show that for any number gamma positive, the expected value over all possible code words that you can, code books, sorry, that you can generate according to that sampling of the probability of error that you care about is upper bounded by two terms. One is the probability that some random variable distributed according to Px Wy given X, and there's a function that involves a log and the ratio of transition probability and Py is less than gamma, plus the ratio of the number of messages that you're trying to transmit divided by 2 to the power gamma. So this is a standard one-shot result for channel coding, but let me tell you how it might connect to something you know, which are the results about channel capacity. So if you want to use that result to prove the achievability of channel capacity, what you do is the following. Instead of just using one use of the channel, hence the name one shot, you use n uses. And you generate your code word according to product distributions, pxn. So you're generating an ID code word of length n according to px. In that case, we're also going to choose gamma, that constant that I don't specify, to be n times the mutual information between x and y minus epsilon. Once you do that, that first term here starts asking what is the probability that the random variable whose mean is I of xy is less than, whose mean is n times I of xy is less than n times something less than the mean. And we know that from concentration of measure that vanishes. Now, if you choose gamma, you see that suddenly the other term vanishes if you don't choose m too large, because m is divided by 2 to the power gamma. So you want m to scale at most like 2 to the n I of xy minus epsilon. So that's why the second term vanishes if 1 over n log of m is less than I of xy. And that's your standard achievability for channel capacity. The reason I'm going through this is because when you talk about covert communication, if you allow me to go back to my slide, everything depends on this parameter alpha n, which depends on the block length. And so unlike the traditional channel capacity where we get to choose a distribution px that is independent of the block length, now it's going to depend on the block length. And therefore you have to be a bit careful about how you apply the channel coding theorem to make sure that there is no funny business happening, is to make sure that you can indeed show that it works as you expect. So it's just a small technicality that requires you to be a bit more careful than your standard channel coding theorem. Now, I want to talk briefly about the converse. I'll go quickly because that part is coming straight from the textbook. So how do you show that you cannot exceed I of xy in terms of rate for channel coding? Well, you start with 1 over n log m. You rewrite it in terms of entropies of w. You artificially introduce the uncertainty of w, the message given the output observed by the receiver. You use Fano's inequality to introduce the mutual information and bound the other terms by small terms. You use data processing to introduce the coded sequence X. And then you do chain rules, conditioning reduces entropy to get upper bounds that single letterize the problem. Okay, so I'm going a bit fast because that's well known. But the point is you end up with a bound that says it's the average over all indices I from 1 to n of your transmission of the mutual information between the input xi and the corresponding output yi, which you can further upper bound using the concavity of mutual information as the mutual information between a random variable x bar, which is the average distribution average across all possible symbols you can get in your code words, but also across time, and the corresponding channel output y bar. Okay, and then finally, you can further the upper bound that by the maximum of all possible distribution px bar, and that's the capacity. The one thing I want to highlight here, and that's the reason I wanted to highlight that converse, is that the last step is a bit crude. We say, oh, we take the maximum input distribution that maximizes the mutual information. But in reality, if you have other constraints, and covertness will be one of them, but if you think about power constraint, you can usually also say something about the kind of distribution X bar that are required. So keep that in mind, because we'll reuse that down the road. Now, the second thing I mentioned earlier is that we'll want to make sure that the code does not reveal any structure from the perspective of the adversary, right? So for uncoded data, we know that we can be covered because we know how to control the fraction of ones. But if you code, you introduce structure, and that structure can be used by the adversary to detect you. So the objective now is to make sure that we can code without revealing the structure, so that the data still looks encoded from the perspective of the channel output of the adversary. It turns out that this is a not so well known, but very old, very old. I think it was first discovered in the 70s. Mechanism in information theory, which consists in the following. Let's say you're given a channel, WZ given X, and you transmit a process which is distributed according to QX at the input. At the output, you get a process distributed according to QZ, which is the marginal of the joint distribution induced by the channel. And let's ask the question, can we replace the input, which is a draw from distribution QX, by coded data? Meaning that there is a uniformly distributed message W, which is encoded into code words X, so that the distribution at the input of the channel is not something as smooth as the distribution QX. It is a distribution that is a mixture of mass points of weight 1/m put on every code word. So it's a very spiky distribution. We transmit that through the channel. We get, again, a spiky distribution, but it is smoothed by the kernel, the transition probability that defines the channel. So I'm going to call that distribution PZ. And then we can ask, is it possible to make PZ close to QZ? So again, we're assuming that W is uniformly distributed. The codebook is known to everyone, and we want to control the relative entropy between PZ and QZ. And again, there's a very elegant one-shot channel coding result, not for reliability this time, but for the output statistics to approximate them. That says that if you generate your code words according to QX, that induces QZ at the output, for all positive gammas, the expected value of the relative entropy between PZ and QZ is upper bounded by two terms. The first term is a probability that some random variable will exceed gamma. And the second one is the ratio 2 to the gamma over m. So I draw your attention on the fact that if you look back at the results on channel coding, this looks like it's a dual. We're changing the sign of the inequality. Instead of m over 2 to the gamma, we have 2 to the power gamma about m. So what does that mean if we start coding over multiple channel uses? Well, if you want to code over n channel uses, you're going to generate your code word still ID, but according to a product distribution QXN. And you're going to choose gamma to be n I of xz plus epsilon. Again, magically, when you do that, you will realize that the first term is the probability that the random variable whose mean is going to be n times I of xz exceeds something that is epsilon greater than its mean. And that probability is going to vanish. We chose gamma just so that it vanishes. Now, if gamma is fixed, how do you choose m? Well, you see that 2 to the power gamma grows with n. So you need to make sure that 1 over n log m, or m by itself, is sufficiently large to compensate the growth of 2 to the gamma. And specifically, you need 1 over n log m to be greater than I of xz plus epsilon. So what it means is that it is possible to generate a code that, even though it's consisting of code words and hence of coded data, completely loses its structure at the output of the channel, provided that you exhaust the capacity of the channel in a way by using sufficiently many code words. Okay, so be careful. This is stronger than saying that beyond the channel capacity, you cannot recover your message. It's saying that beyond capacity, certain codes have the ability to completely lose their structure, meaning that you cannot tell that the data was coded. It looks like it was sent from a distribution that is smooth. So there's a very elegant converse associated to this approximation of output statistics. And since we took a little bit of delay at the beginning of the tutorial, I'm going to skip it. I will include it in the slides, of course, and below are the references that address it. The reason I wanted to cover that at the beginning is because there's something very elegant about that converse proof. The credit should really go to Jehu, Gerhard Kramer, and Ligong Wang. They are the first, in my opinion, who developed it. It's a very elegant way to go from operational constraint on a relative entropy to being able to say something about the minimum rate that's required. It has the spirit of the converse of channel reliability, meaning you're single letterizing your expressions. But of course, there are some technicalities, but there's a very nice recipe that is effectively playing the role of Fano's inequality for reliability. So I will skip that for the sake of time. I'll apologize for that, but I'll be happy to go over that at the end of the tutorial if we have a bit more time. It's not crucial to our discussion. All right, so where are we right now? We know three things. We know that we have access to this notion of covert stochastic process, which is uncoded RID, that allows us to identify the optimal fraction of ones we need to transmit to be covered. We know how to code for reliability through channel coding. We also know how to code for approximation of output statistics through a modified channel coding argument effectively. And now we're going to put all these three together to prove the result on the covered capacity of a discrete memoryless channel subject to a relative entropy constraint. The key insight to develop to get there is to understand what is the structure of the coding scheme that we're going to use. And I'm going to give it to you. I'm not going to try to motivate it. I'm going to give it to you and we'll check that it works. So what we're going to do is we're going to design a bank of encoder-decoder pairs, which are matched for reliable communication. So to every encoder on the left corresponds a decoder on the right. So when Alice has to transmit a message W, she sends it through all encoder-decoder pairs. But which code word is being transmitted through the channel is decided by the secret key S, but is shared by Alice and Bob. So the secret key S decides which of these code words at the output here is being sent over the channel. Now, from the perspective of the legitimate receiver, the only uncertainty is in the choice of W because it knows what is the secret key. Therefore, it knows which encoder is being used by Alice. However, from the perspective of the adversary, the uncertainty is in both the message W and the secret key S. And so as a result, from the perspective of the adversary, Willie here, it looks like there is much more uncertainty about what was sent by Alice than there is for Bob. And so what we're going to do is we're going to play with that as follows. We're going to choose the rate of the codes, encoder-decoder pairs for reliability, to be such that Bob can decode. And we're going to choose collectively the code words in all these encoders here in such a way that they form a code that loses its structure from the perspective of the adversary because you're transmitting above the capacity. And so the secret key here is used to create that asymmetry in the number of code words that can possibly be transmitted at the channel from the perspective of the adversary. So let's try to be a little bit more formal, and I'll go and show you the entire proof here. How do we transform this discussion, which is fairly heuristic, into something formal? So I'm going to give you here a template that you can use to actually prove results for covered capacity, and it's been used by myself, of course, and many other collaborators and colleagues. So step one, we need to find the fraction of ones that we need to send through the channel. And based on the lemma I showed you earlier about the covert stochastic process, we're going to choose alpha n to behave like 1 over square root of n, but the constant we're going to choose to be exactly square root of 2 delta over chi2 q1 q0. But applying the lemma I showed you a few slides ago, that guarantees without any calculation that the relative entropy between the encoded covered process q alpha n and q0n is essentially delta. All right, so alpha n is the right fraction of X1 code symbols to use to get the covertness with level delta. Now, at the same time, if you compute the information rates between X and Y and X and Z, you get exactly the quantities that show in the theorem. There is a square root of 2 delta over chi2 divided by n here, times the relative entropy, and similarly for I of xz with q is replaced by p. Okay, so again, these weird terms are actually just mutual information in these guys. So, okay, we have the right fraction of ones. Let's use that in the channel coding theorem. Well, we're going to apply it. As I said, you can apply the one-shot coding theorem I gave you before for the specific distribution Bernoulli alpha n, product n times, used to generate the random code words. And the math goes through, and you can there show that there exists on average, the code will guarantee that your probability of error decays like an exponent minus something times square root of n, as long as you don't transmit too many bits, which here takes the form the log of m divided by square root of n delta less than square root of 2 chi2 times d. But again, I want you to realize that that quantity that I'm highlighting here on the right is just a mutual information I of xy in this guy. Now, similarly, we want to guarantee that even though we have coded for reliability, we don't reveal structure to the adversary. So we're going to guarantee simultaneously that when we apply random coding for the approximation of output statistics, still with code words generated according to that distribution, now that argument applies not to subcode books, but to the entire code book, the expected value of the relative entropy between the coded distribution observed by the adversary and Q alpha n, your non-coded data or non-coded process, if you wish, is going to be essentially going to zero very fast with n, as long as you use enough code words to overload the capacity of the eavesdropper channel, which here takes the form, the sum rate of log mn plus log kn, normalized by square root n delta, as to exceed the square root of 2 over chi2 times d q1 q0, which again, I want you to understand as I of xd in this guy. So I'm really just applying the one-shot coding results here to the specific distribution, which is Bernoulli with parameter alpha n, id over n channel uses. And once you've done that, you can show that if that's true, there exists at least one code such that the relative entropy will be essentially delta, the probability of error will be small, and you will be able to choose the number of bits log fmn divided by square root of n delta here to be less than this quantity here, which is the covered capacity. And you can get as close as you want, as long as the number of key bits satisfies that lower bound. Okay, so that's the framework that we use to prove these results. Identify the fraction of ones and apply coding theorems to code for reliability and make sure we don't reveal the coded structure to the adversary. So that's the achievability proof. You can convince yourself if you go back a few slides in my deck that these are indeed the limits I announced. Now we also need to make sure we prove that we cannot do better than that. And then again, what we're going to do is we're going to apply semi-traditional tools to get there. The one unusual step is the one where we say that given a coding scheme that guarantees covertness in terms of relative entropy being less than delta, we can say something about the fraction of one. So that's the non-trivial step in the converse proofs for channel for covered capacity. It's possible to show, and I'm skipping it for the sake of time, but it's not too hard to show that if the relative entropy is less than delta, it imposes a bound on mu n, the fraction of one that you can transmit at the input, which turns out magically to be the one we had identified in the achievability. So, you know, things work well. I'm claiming covered capacity, so it's not surprising. Once you have that, you're going to plug that constraint into your analysis of the reliability converse and single letterization to get a bound on the ratio log mn over square root of n delta. I'm not really hiding anything here. If you do that step, if you plug that bound here in the converse I highlighted a few slides ago, you will get to that result. And similarly, you're going to use a standard resolvability converse, use the fact that you know that now the fraction of ones at the input is bounded by this to show that you get a lower bound on the log mn plus log kn over square root of n delta, which conveniently is the one we had in the achievability. So the converse matches the achievability, so we have a full coding theorem. And as you can see, it is somewhat standard in some way. We're using known approaches and tools, but I'm using mechanisms and combining them together in a fairly non-standard way. The good news is that that approach generalizes conceptually to other metrics, including the variational distance, which, as I mentioned multiple times, is the one we should care about. It also generalizes to continuous channels such as AWGN channels. And the only difficulty is that the proofs get slightly more intricate and involved, and that's why I didn't want to go into them. You can check the papers listed there if you want more information. The one thing I should mention is that, interestingly, if you want to analyze the converse for variational distance, it ties quite nicely to the fairly nice conceptual approach that Bulat highlighted in part 1, where he's thinking about it in terms of the detector of the adversaries. So it's kind of closing the loop nicely with the intuition he developed when we started working on the problem. So everything works well. I should mention though that converse for resolvability get more challenging if you're not using relative entropy. So yeah, that's a framework for how you prove covered capacity. That's the reason why you have this weird scaling. That's the reason why it depends on delta, but we now have a very clean framework that we can use to develop the proofs. So at that stage, we've kept you entertained for an hour and 40 minutes. So what I would suggest is we take a 5-minute break, so that if someone wants a bathroom break, we can do it. So I'm going to stop here. It is exactly 6:50 Eastern time, so we'll resume at 6:55 on my clock. So in 5 minutes, if that works for everyone. And in the meantime, I'm going to stay here. So if there are questions, I'll be more than happy to address them.
Yeah, thank you, Bulat, and thank you, Matthew. So we will, as Matthew said, so we'll be back in 5 minutes. So I think there is one question in the chat box that Bulat actually referred it to you, Matthew. So
okay,
if you can answer that.
Yeah, the one-shot coding results, I think Adrian asked whether they can be used over and over again. And I think they can. Of course, in covertness, you're going to have to be very careful because your distribution changes. But even so, as long as you provide for the...
So let me see who...
this is the last
okay,
question.
So the question is from Adrian. Are you still here, Adrian?
It looks like he's here. He's muted.
Okay, just to make sure that I'm replying to the question. So you're referring to the one-shot coding result, right? Let me show it here. This one, right? Okay, so I think the question has to do with, what is the meaning of the one-shot result, and let me share my screen again. Do you still see my screen, Bulat?
Yes, yeah, we can.
Okay, all right. So the question has to do, I think, fundamentally has to do, and correct me if I misunderstand it, with how do we use that result here? So the way you should think about the one-shot channel coding result is it is a way to think about what random coding does without having to worry about the fact that when you actually code for real, you're using multiple channel uses. Like, in a way, the framework is super abstract. So whether X here, what I code, is really a scalar or is a vector is completely irrelevant to that framework here, right? It's very general. I'm totally free, when I choose the distribution Px by which I generate Px X to introduce an N if needs be. So you should think of that one-shot result as encompassing everything you need to know about random coding for channel reliability. And then when you want to use it to really understand, okay, how many bits do I get per channel use if I code over many, many bits, you're going to take that one-shot result, but instead of using a distribution Px, which is scalar, you're going to use a distribution Px, which is vectorial. And specifically here, I choose it to be not only just vectorial, but also a product distribution, because that allows me to control the first term very, very cleanly. So to answer the question, hopefully correctly, what I'm telling you is that when you go from one shot to multiple channel uses, it's not that you apply the one shot channel result multiple times, n times. You're still applying it one time, but you apply it at once on sequences of length n as opposed to scalars. So I hope that answers the question. Okay, now I'm looking at the questions. I think Bulat already answered.
Hello, Matthew. This is Srijit here. I have a question about
Go ahead.
1 over square root and scaling. So is this somehow related to the central limit theorem somehow, like linked to?
Yeah, it is exactly related to the central limit theorem. And so I have different ways of articulating that, if you wish. So let me go back to the presentation. I'm going to give you two ways to answer it, one intuitive and one mathematical. Just let me know if you don't see my slides, but I'm back at that little slide 27 where I tried to articulate heuristically what's happening here. So the reason it's related to the central limit theorem is as follows, right? So we're trying to find the fraction of one that will still guarantee covertness, but we know that the CLT kicks in. It says, like if, for instance, the adversary were to try to estimate the mean of the distribution that it expects when Alice transmit, right, which is bimodal, we know that that distribution can be estimated if you get n samples and you get the mean quite accurately, but there is a standard deviation associated to that, which is in square root of n. Okay, and so what we're doing is we're choosing the fraction of ones to be such that you're lost in the statistical noise. Okay, so that's my first answer. Now, to connect that to central limit theorem a bit more cleanly, what you have to do, I think, is you have to, okay, let me use this one. If you look at the one-shot coding theorem, right, we know that, that when you apply these results, you're looking at the probability that the random variable concentrates around its mean, right? So that variable here, what's happening is I'm choosing, very carefully all the quantities here so that I'm always lost in the deviations around the mean. And I think mathematically that's going to show up very, very clearly if you write, how you bound that using a concentration of measure inequality very clearly. So intuitively, that's the diagram I gave you. More precisely, that's given because you have explicitly a quantity where you look at the probability that some random variable deviates from its mean in the random coding arguments. And so that's why it's innately related to the central limit theorem, if you wish. Does that make sense?
Yes. Thank you.
Sure thing. All right, so I think everyone is back. So I think we can go and start talking about part 2B. So Bulat, we're quite behind on time, right? So I think we're finishing in half an hour. Is that correct?
Yes. Yeah.
Okay, so I'm going to try to make it quite fast, Bulat, so that you can use the rest of the time.
And we can cut some of part 3 out as well, so we can skip some parts. So yeah.
Perfect. All right. So let me dive right in that case. So I want to touch upon how we can now design covered capacity achieving codes, right? We know covered capacity. I give you the framework by which we can establish covered capacity, but how do we design codes? And there are a number of challenges, and rather than get into the details of how we actually design a concrete code, I'll just allude to it. I'll show you the path that we've developed, at least in my research group, to kind of understand how we can leverage the intuition from the information theory. All right, so what have we learned from the information theory, right? So the main message that hopefully everyone has gotten at that stage is that if you want to be covered, you have to use low weight code words in which the fraction of non-innocent symbols, so what I called x1 before, has to be 1 over square root of n. We know that's required if you want to be covered. Now the challenge is it's not too hard to show that if you were to use an NK binary linear code that you use over a binary input discrete memoryless channel, and you assume that all messages are used at random uniformly, you can always at the detector design an hypothesis test that will detect the presence of the code extremely well. So specifically, it's possible to show that the probability of false alarm and the probability of misdetection, they essentially behave like 1 over the dimension of the 1 over k, the dimension of the code. So it goes to 0 super fast. You can always detect. And what's behind that lemma is actually a known result, which is that if you're using a linear code, you look at any given position of your code words, you should expect 50% of the time you get to 1, 50% of the time you get to 0. And so what that lemma here is telling you is that if you want to be covered, you have to use some nonlinearity. because families of pure linear codes without something else will never get you to the covered capacity and will never be covered, actually. And people have looked at many different things. Me and my group have looked at using Polar codes, invertible extractors, that's what I'll talk about. But some other folks, and I think in particular some of the folks here on the tutorial, if I've looked correctly, I've used LDPC codes and some really tricks to control the weight. There's a very nice work by my colleague Eric Zhang, Jaggi, and Mayang Bakshi, in which they have shown that at least conceptually, if you can in principle use a concatenation of a short code with a rich Solomon code and still be covered. And so I won't do justice to all of that. I'll focus on the path that we have followed in my group, but we have what I think is a low complexity, provably optimal, at least asymptotically, construction of codes that matches the theoretical results I derived before. So if you've done coding, you know that coding is possible because you have structure, right? The reason people like to introduce non-linearity when you talk about coding is because linearity is a nice structure that you can use to simplify the decoding. All the decoding techniques using information theory, maximum likelihood, typical set decoding, or the one that is implicit in my one-shot result, which is called threshold decoding, they're not at all realistic. So you like to have structure. So what we're going to do here is we're going to try to introduce structure by changing the way we transmit data. We're going to try to enforce covertness, not just through coding, but through signaling. What I mean by that is instead of trying to use a fraction of 1 over square root of 1, that is kind of randomly spread over the entire length of your code words, we're going to put structure in the following sense. I'm going to require that I use pulse position modulation, meaning that I'm going to require that every m consecutive symbols I send, exactly one of them is a symbol x1, the other are zeros. That's called a pulse position modulated symbol. If you have a ppm symbol of length m, you get m distinct symbols by changing the position of the one. Okay, so I'm going to require that. And so if I create a sequence of ppm symbols to code, say a sequence of length L, it's going to be L consecutive blocks of size m. And in each block of size m, I know that I have one and only one symbol x1. Now, what I'm going to also imagine, if I want to do uncoded transmission over ppm symbols, I'm now going to choose my ppm symbols uniformly at random, which probability 1 over n, and I'm going to transmit that through the channel. So in a way, you choose a ppm symbol uniformly at random, so 1 over m, and if you look at the distribution you get, it takes the form of that mixture that I'm describing here. Okay, so I'm going to call that a ppm process. It's the process perceived by the adversary when you send one ppm symbol at the channel input chosen uniformly at random. Now, you can prove a nice result that shows the following. If you look at, from the perspective of the adversary, what is the relative entropy between that ppm process here, qppm at, and q0m, which is what the adversary expects when you're not transmitting, you can show that it behaves as 1 over 2m times the chi-square distance between q1 and q0 plus some, term that vanished to 0. ppm symbols, every time you choose a ppm symbol uniformly at random, use L times in an independent manner. So you look at the product distribution L times of the previous distributions. You see that you're going to be able to bound the relative entropy between the processes where you transmit ppm symbols and the process Q0 where you don't do anything by a quantity which is L over 2m using the additivity of relative entropy times the chi-square plus some term that should vanish. So what this is showing you is that when you use a ppm process that has much more structure than me choosing the position of the ones according to a Bernoulli alpha n, where alpha n is 1 over the square root of n, I can still get the same effect by choosing very carefully how L relates to m. In particular, if L is proportional to m, right? The total block length, which is L times n, is going to be m squared. So that means that you can really understand L and m as being scaled like square root of n. And so that little lemma here is the counterpart of that lemma I gave you a few slides ago on the Covert stochastic process where you have a Bernoulli input with a bias on the choice of one, which has much more structure. So why do we care about structure? Well, if you think about my encoded data here, it's not that my encoded data is based on a biased distribution. My encoded data is based on a random choice uniformly at random over ppm symbol. So it's uniform. the bias that I need to get covertness is completely captured by the structure of the ppm symbol itself. And so coding over, something that's supposed to be uniform, that I like, because that's what linear codes do. They guarantee you that you choose, over symbol that you have access to uniformly. So that's the reason that we started looking at ppm, is because it translates the bias problem from the actual code to the symbol that we're using and over which we code. Now, of course, there's a catch. The catch is that if you follow my argument carefully, if I want to scale everything and the block length, now the length of the ppm symbol grows with the block length because it scales like square root of n. So that means that if I design a code, I would have to design a code over a non-binary field, or it might not even be a field, that has a length L that grows with the block length n. So if you know Reed-Solomon codes, you know they're query codes of length q-1. So it's not completely crazy to think about coding with a length that depends on the field size. However, what is a bit more crazy is to think that you can scale the field as much as you want, because we want to scale the block length. And so I've introduced a nice trick here, but it looks like it's not super usable. So how do we go around that? So what we're going to do is we're going to use multi-level coding with multi-stage decoding. So multi-level coding refers to the idea that instead of trying to directly code over non-binary symbols, we're going to code over binary symbols, and we're going to generate independent coded sequences of bits. And the bits that you get in each code word, we're going to map them together to index a ppm symbol. So as an example, I'm going to assume that my m, the length of my ppm symbol, is a power of 2 to the q. So it means I can describe m by q bits. Okay, and so I can represent that by q levels. I'm going to code each sequence of bits independently, and then I'm going to glue them together. And for instance, if I get 3 zeros at each level, I'm going to decide it corresponds to ppm symbol 1, 100 it's symbol 2, and so on and so forth. Okay, so that's a strategy that maps binary code words into a non-binary coded sequence. Now I'm going to send my ppm symbols over the channel. So I put a tilde here because these correspond to the channels viewed by the ppm symbols, which are themselves, m of length m basic symbols over your original channel. And at the receiver, I'm going to assume that Bob is going to do what's called a multi-stage decoding, starting from level Q, meaning he's going to first try to estimate, okay, what was the message coded by the last encoder Q here, assuming you decoded correctly. Let me try to estimate the next WQ-1 and all the way back to W1. You can think of that as a successive cancellation decoder. And we know from results from the 90s that this is actually optimal in principle. So what we're doing here is we're transforming the problem of coding over non-binary symbols whose length grows with the block length into a multiple access problem. You can think of every level as one entry into a multiple access channel that consists of the ppm mapper plus the true channels. And so we don't have to code over non-binary symbols anymore, but of course the number of levels, which is Q, is going to grow because m grows like a square root of n. So we've just translated the problem again. So it looks like I'm running in circles, but believe me, I'm actually going somewhere. You can think about, okay, it's okay, I have to code here at each level, but what is the capacity or what is the rate of the code I have to use at each level? So it's possible to define the capacity that each binary input level is seeing. So that's the capacity. You can think about it. I'm not proving it formally, but it's given by the mutual information between Bernoulli half variable xi at the input and the channel output, given that you have decoded the previous levels, which in my case is I plus 1 to q because I start from q. Okay, so this is the capacity of the bit level. It's possible to analyze it precisely, and what's interesting is that it decays extremely fast with the index I. So to illustrate that, I'm looking at a binary symmetric channel with crossover probability 0.1 and 16 levels. If you compute these capacities, what you will see is that level 16 has like nothing capacity, 110 to the -4. It's very slow to increase as you go up in the levels, or go down, sorry, given my labeling. And only the last few levels actually carry any meaningful capacity. So what this is telling you is it's telling you that even though we're doing something weird, right? We're transforming this system into a humongous multiple access system where we have tons of these levels to code over. Actually, only the lowest levels carry any meaningful capacity. And so in actual effort for code design, all we need to care about are the first few levels. The others, we know they carry nothing. What's the point of working hard to design a code when you know that you can transmit at most 0.0001 bits? So the challenge is still, okay, given that, I hope I've convinced you I only have to code over the lowest level. How do I do that? Well, the last challenge that is there is that because everything that I do depends on the block length. In principle, the moment I change the block length, I change the number of ppm symbols, I change the length of the ppm symbols, I change the number of levels I code over, and potentially I change the capacity of the level I code over as a function of the block length. And that's bad news, because traditional coding doesn't work like that. Traditional coding, you're given a channel that is independent of the block length, and then you increase the block length to improve your coding performance. And the reason we went through all these hoops here is that magically, actually, this is what's happening here. So coding is actually hugely simplified because using that multi-level coded structure together with multi-stage decoding, you can prove the following two results. One, from the perspective of coding for reliability, at each level I, you only have to worry about coding for a channel whose expression I give here for completeness, that's exact. But the important part of that expression is that it does not depend on Q, the number of levels, and therefore on N, the block length. It only depends on the index of the level. And the lower the index, the simpler that channel is actually. And so what it means is that if you code for that channel in the multi-level coding, that means coding at one of these encoders, you code for a channel that is fixed, even as you vary the block length. And therefore you can use traditional code that you like, such as Polar codes. Most importantly, the same result holds when you want to code, not just for reliability, but also to guarantee that you approximate the output statistics. But remember, our goal is still that we have to code to guarantee covertness and lose the structure. Again, what can prove that the coding for ensuring that we don't disclose the structure of our codebook happens over a channel to the adversary this time that is, again, independent of the block length. So magically, this complicated structure that we came up with is one that gives you the ability to convert the problem of biasing the weight of your code word and hiding the structure for a complicated channel model to one in which it's almost coding as usual. I say almost coding as usual because I still need to show you that the proof is in the pudding and we can actually design actual codes. And for the sake of time, I'm not going to go into the details, and I didn't want to go into the details anyway, but I want to convince you that it's possible to code for reliability. That I think you've already accepted by coming to ISIT. We have LDPC codes, turbo codes, Polar codes. But I'm also going to argue that we can code to achieve the approximation theory of the output statistics. That's much less obvious. That's much more recent work that's leveraging ideas coming in part from computer science. People know how to do that because they're very useful in the context of coding for the wiretap channel. And I just want to highlight that there are a couple of people that have really played a key role to push these ideas. Belare, Tesaro, and Vardy had some really influential paper in 2012 showing how to design that. Masahito Hayashi has done great work in that space. And all of that is really nicely exposed in a paper by Tiagi and Vardy that I encourage you to look at, because it really gives you a nice perspective on how we can design these channel resolvability codes using tools from computer science called invertible extractors. And lastly, one of my students and myself, we've looked a lot at Polar codes, and we have shown that we can actually achieve that effect with Polar codes. And so at this ISIT, one of my students actually presented a code construction for covert communication that combines all of these ideas and results in a real code. So the length of the code is large, but essentially is able to design a system in which you're using partly Polar codes to code where the data is there, or sorry, where the capacity is there for the lowest level, is using Polar codes with least decoding. So there's a CRC there, and is achieving resolvability, approximation of output statistics and reliability jointly with Polar codes. And so for the details, you can check his papers. For the levels where we know there is no capacity, we still need to make sure that we don't have structure for the adversary. So he's using a code that is just for output statistics approximation that is based on truncated invertible extractors. And he's able to design what I think is the first code for covert communication over binary symmetric channels. I give you that. That is efficient in the sense that it actually transmits more covert bits than it actually uses secret key bits. And that's a significant departure from some of the first results that Bulat had obtained, in which he needed a lot of secret bits to ensure covertness. So I went a little fast here. I'll be more than happy to follow up offline after the tutorial if you have questions on the coding part, but I'll stop here so that Bulat gets a chance to highlight some of the really cool research direction that people are looking at in covert communications beyond the covert capacity and the coding that I presented here. Thanks a lot, guys. And Bulat, back at you.
So we cannot hear you, Bulat.
That I was actually saying, Matthew, there was one question was asked by Neil that what is the secret and all the PPM stuff is on the diagrams. I think you can maybe address that and have a minute, and you're muted, like I was.
Okay, so the question is about the secret key.
Yes, where is it in the PPM schemes?
Okay, so to make a short answer here, conceptually, the coding scheme works exactly like the overall coding scheme I highlighted, where you have this bank of codes. I did not detail it here, and the example I give at the end is for a channel where you don't actually need much secret key, but you use the secret key to change a little bit how you create the code words. So that's not at all in my slide, and for that we would have to go into the details of the papers to understand where the key is used to create the code words. But conceptually, the fact that we use PPM, we could use a secret key just to randomize, which pair of encoder decoder we're using. So that conceptually works exactly as I highlighted in the information theory part.
All right. So Mayar and Laura, and if others, so we only have 15 minutes left in the official part. I'm wondering if we can go over if folks want to stay for just additional, 10 minutes or so. It's would that be okay? Or is this?
So Laura, I think Laura can create a breakout room. So because I think there are some other live session as well.
Oh yes.
So would it be
yes.
possible, Laura, to create a breakout room after this session so we can move there?
I believe it is, because that's been done for the conference talks. So let's do that.
Yeah.
Let me get through as much as I can, and then we'll finish in the breakout room for those who are interested. Does that sound good?
Sure. Yeah.
Right.
Yeah. Great.
So let me. I'll start by stating that we have up to now had the Willie decide between normal environment, which is H0, and Alice transmits in a normal environment in H1. And this environment did not change at all throughout. So there was nothing dynamic about the channels, abstractly speaking. And what we're gonna try to do next is include these dynamics, channel variations that could be due to just external factors like jamming, interference, etc., in the covered capacity calculations. We're going to see that it radically changed the picture. So what happens is that while the fluctuations in the channel and noise in the channel are quite harmful to standard comms, they're extremely beneficial to the covert comms in that the screwed law goes away in some cases. And the key idea is that it doesn't allow Willie to set up a proper hypothesis test. So it's something that has been underexplored in IT community, I feel, and that's how I'm trying to bring it to bear here. So let's take the picture of the additive Gaussian white noise channel that I've shown you in part one of the talk, and assume instead of sigma W squared, the noise in the adversary being fixed, let's assume that it's random variable. In that case, you can transmit order square root of n bits. I should have said bits instead of blank in n channel uses if Willy uses a regiometer. And this implies that for this particular case, there's positive channel capacity. And this was first observed by Lee and Baxley in this, well, previously had conference papers, but this is a journal version of this paper. And the main weakness of this very interesting result is that it restricted Willy to a specific detector. It turns out that for the particular problem they looked at, regiometer is actually a optimal detector, which we have proved later, but it takes some work to prove it. But this should give you at least a hint of of how beneficial the variability of noise is to the to core communications. So continuing forward, now in most cases, what would happen is that the Alice will have some fixed period of time when she transmits, and the channel is going to be fairly constant for quite some time. So let's suppose that the time that Alice has to transmit is significantly smaller than the period of variation of the channel. So the channel is constant over this segment of T of n blocks, and she has to pick a block to transmit on, and she has to use consecutive symbols to do it. In that case, we're back to the square root law. It's slightly different. It's square root of n times log of T of n, and this is called a synchronous square root law. Details are in these papers. But the point is that Willy can estimate the sigma w, which is random, from the T of n minus n blocks that Alice does not use, even if he does not know which block she uses. And that's a neat result. So there is a the variability of the channel is rather fragile in that sense. But let's continue, let's move forward and see what happens if the power of the noise at the Willy is changing during the cold wave transmission time. So for that, we're going to introduce this model, which is an uncooperative, uncoordinated cooperative jammer, which basically transmits white noise, white Gaussian noise, onto the channel, both to Bob and to Willy, and he picks the power of his noise uniformly from between sigma squared min to sigma squared max. And he changes it, picking a new power every n divided by f of n symbol periods. So he does it over f of n times, and f here stands for phasing, but which is the reason is because it's motivated by a block phasing model from wireless comms. So now I have to say that this model, the uniform distribution model, is not particularly important. We can show the same results that I'm going to show right now for other distributions such as Rayleigh. And also the cooperative jammer doesn't have to be cooperative. It could be a jammer was placed there by Willy to prevent the communication between Alice and Bob from happening in the first place. Well, if Willy doesn't precisely know what the jammer is transmitting, then he cannot subtract it out, and thus if there is any kind of phasing on the channel between jammer and Willy, that means that there's random power changes, and that means that magically, not quite magically, but the amount of information that Alice can transmit to Bob goes from square root of n to n. So essentially, Willy is shooting himself in the foot. So uniform was picked for convenience here. So the question is, fundamental question is, looking at this number of changes in the channel while Alice is transmitting, how does it impact the covert capacity? How does it build the number of bits we can transmit covertly? And it turns out that there is different gradations of f(n) where different results arise. When f(n) is much smaller than 1, it corresponds to the asynchronous square law that we have seen earlier. Essentially, the times that it varies isn't much larger, could be larger than the n in the block length that Alice uses. So we go back to square root law. So this is not a very good case. We've seen it just now. More interesting case is what happens if f of n varies a lot. That means that Alice's transmission is long, so she's there for a long time, and or perhaps the phasing happens very fast, or the jammer is configured so that it fluctuates its power fast. In that case, it's conceivable that the adversary can average out the fluctuations and still detect errors. And that's pretty much what happens. And it turns out that f of n being a constant, either 1 or some constant greater than 1, is just right. It's in that what's called the Goldilocks zone, for those of you who are familiar with Anderson's fairy tales. That means that's when the O of n covert bits can be reliably transmitted. So let's go into the results. First, achievability approach. I'm not going to go into the proofs here because I just don't have the time. I'm going to just detail the approaches that we use to create those proofs. And unlike what we presented to you in parts 1 and parts 2, we're not going to bound the detector's performance by symmetric. We will have to characterize the optimal detector. At least that's what we can do at this point in what we've been able to do in information theory. There is a we have not been able to find the bounds that work on the optimal detector for Willy, so we had to actually characterize how it looks like. Now, this is not the we don't think this is the consequence of a problem. I think it's a consequence of us not finding the right solutions. So, all right. So then, once we characterize the optimal power detector, the optimal detector for Willy, we can determine the signal power of Alice that she uses, and then use standard coding techniques to transmit information using them. And by standard, I also am going to encompass the codes that Matthew presented for the covert channels, because those will work in some cases too, including the asynchronous case. They'll work. So these are the papers, the key papers that my colleagues and I wrote on the subject, and I will point them out to you. So let's see. First, let's examine a case where F1 is 1. So the jammer chooses a random power to transmit, and at the same time, Alice can start transmission. And this turns out that you can show that radiometer is optimal. This is the case that Lee and Baxley in that first paper I showed you as the case that they examined. And it turns out that radiometer is optimal, and you can transmit all of n bits in it. But it also turns out you can do all of n bits when F1 is a constant. But in that case, radiometer is not optimal. And the key technical tool here is that certain mixtures of distributions preserve the likelihood ratio stochastic ordering. And this is in this book, Stochastic Orders and Applications, and we can show that the Alice's transmit power symbol need not decay with n. Now, I think we're out of time here, so I think we're gonna try to move to the breakout room if Lauren has made one.
Sorry, Bullet. So you can keep going, but if you can try to shorten your presentation, you still have a few minutes, but we can stay here for maximum 30 minutes. But I think if you can try to slightly shorten your presentation, and we have time maybe for some question and answer at the final.
Very good. I will let me take another 10 minutes or so to do this. Will this be continued to be recorded? I hope it is, because we'd like to have there's some folks who are dropping off. So
Yeah, it's been recorded. Yeah.
Okay. Okay, so very good. So the technical tool is in this book. It's in chapter 1 of this book, and we're glad to find it. And it turns out we can use it to show optimality of power detector for f of n one case, as well as show properties of it enough to get the ON power. The interesting thing happens is when f of n is increasing with block length n. That corresponds to the fades being relatively fast relative to the message. So for the converse, we can give Willie a radiometer, and Alice can then only use one of square root of f of n power, and reliably transmit square root of n times divided by square root of n, square root of f of n Covert bits to Bob. So this is sort of like a screwed law. Now we're back to the screwed laws. But the problem with this is that the achievability is difficult. So achievability, what we have done so far is, first of all, we do not know that optimal detector. What is optimal detector for this? We know that the radiometer is not optimal, but we don't know what optimal is. The theorems that we have used with the stochastic coordinate don't actually give us a structure. So let's assume that there's a genie that gives Willie additional information. What it gives is a vector of powers that Willie observes on each of the blocks, and the power is a total power, which is the power at the Willie, which is at this point is constant. And notice that the randomness comes from jammer. The instance of jammer's power in K subblock, so the instance of sigma K squared, as well as PA if Alice is transmitting. Obviously, Genie doesn't tell Willie that Alice is transmitting. That would make Willie's job really easy. Just tells the total power. But in that case, the distributions are basically marginalized, and the observation gets marginalized out. So at that, when Genie gives Willie the power vector, the observations themselves become unimportant, because conditioned unknown power, they're just normal random variables. It's not all, they're not all innocent. And when you take like ratio to obtain the optimal detector for Willie, they get divided out. So all that matters is the sequence or the vector of powers that Willie receives from Genie. And some math later, we can show that to avoid detection by this Genie aided Willie, Alice must set the power to 1 over f of n, and transmit only n divided by f of n covert bits. And this is in the Spock paper by Dennis and co-authors and me. So in summary, Willie with the radiometer allows us to transmit this amount of bits. That would be the upper bound. Genie is really, this should actually be lower bound. This is a big omega, I guess. Lower bound is n divided by f of n. You can see that there is a rather large gap between the achievability and the converse, and we think that the achievability is the one that's loose. It's the information that Genie provides Willie is incredibly valuable. And if f of n increases quite fast, then the subblock number of readings that Willie receives in subblock would not be enough to actually estimate what Willie needs to know. But we don't know how to close this gap. It's an open problem. So For those of you who are interested, you can chat with me later. So that concludes the general assisted covert comments. Let me go and jump into the quantum, and I'm going to have to cover quantum covert communications in about 5 minutes. So maybe I'll have 7 minutes or something. It's okay. So this is the motivation for using the quantum analysis. And briefly, it is this. When we have our standard memoryless classical channel, it's really a consequence of taking a memoryless quantum channel and choosing the modulation scheme and measurement. That's all. And any kind of a memoryless classical channel, if you go and dig deep into it, dig what's in the box, it's a quantum channel with the modulation that translates the classical symbols into states, and the measurement that translates the states into the classical output. And obviously there's randomness involved in measurement, especially as well as the channel itself. So why do we care about quantum? Well, it's because it gives us additional degree of freedom, in that we can choose the measurement, we can choose the states, we can employ quantum resources, entanglement between the transmitter and receiver, and this helps throughput. It also allows us to perform security analysis against the most powerful adversaries who have access to the tools we mentioned above, as well as possibly control of Alice 2 channel, which is this quantum channel here. And I will not have, I have zero time to go into any confirmation theory, but I would refer you to 2 wonderful tutorials were given by Mark Rossi in 2016 Barcelona at SIT, and Saikat Guha in Vail in 2018 SIT on the quantum information theory in general and quantum information theory pertaining to the optical communications in particular. And you can think about this as this is the discrete and this is continuous information theory. So that's how I would break it down. There are also many resources on the web, and my favorite ones are listed here. But you can find a lot of information on this stuff. So let's see. Let's talk about the differences between QKD and covertness. QKD generally assumes that the adversary controls the channel. It turns out that if he does so, then covert communication is impossible. I'll give you a practical reason why in a couple of slides, but intuitively, it's because there is no way to hide if all the noise belongs to Willie. And Willie, by virtue of controlling the quantum channel, controls the noise. And this was really nicely proven in the 2 papers by Meredith Ahmasbi and Matthew. And I had alluded to this in my early 2015 paper. So we have to assume that there's some lack of control of the noise by Willie in order to have covert communication to begin with. So from this point on, we're going to assume that Willie doesn't have control over the memoryless quantum channel. That's what we're going to assume from right now. So and this is in contrast to QKD. So we're going to take Willie out of the channel, and we're going to give Alice and Bob some pressurized secret key, and we're going to restrict Alice to finite dimensional product states, meaning that she's using a state that's not entangled between the channel uses. And we're going to take the innocent symbol, again, designated, and using exactly the techniques from part 2A of this tutorial, we can adapt them to characterize the core capacity of this particular circuit. And the key technique here is quantum channel resolvability, which is described in Masahiro Hayashi's book, as well as papers by him and others, and this was all done for ISAT 2016 by an intern in my group and a graduate student at UMass as the Shilstami. So we get a school law. So I will say before I leave the slide is that the general input problem is still open. We believe the school law holds for it, but we don't have the capacity results. It is very hard because level information is superative over general channels. So it's not a easy road to hoe to prove this. So now let's look at the bosonic channels, which you describe quantum mechanically, optical, microwave, RF, really any kind of a channel deals with electromagnetic radiation because electromagnetic waves are quantum mechanical. And no transmission state here is vacuum state, meaning that Alice puts vacuum into this channel. And then we're gonna assume that there is thermal noise on it. This can be from the sun, from other sources of electromagnetic radiation, or from the black body radiation at the receiver itself. And this kind of a channel is also known it's a subclass of a Gaussian channel, but it's very much like an additive white Gaussian noise channel in the classical information theory. And what we have is we can first of all generalize it to more than 2 inputs and outputs with some care, of course, by appropriately adjusting this beam splitter. And so the channel, it looks like there's a beam splitter. One port is thermal noise, another port is your input, and there are 2 output ports. One goes to adversary, another goes to your legitimate receiver. And we can generalize the beam splitter to have more than 2 inputs and outputs. And as I said, it's a quantum analog way WGN, and choosing coherent inputs and coherent receivers gives you a WGN effect. So let me briefly describe the results for covert communication with this channel. When you have no noise that's added, when the channel is called pure loss, meaning that the environment is vacuum, then there's no where to hide information. So there's no covert communications possible. So this means that if Willie has control over the environment, like a QKD analysis, all he has to do is turn the noise off, and then he'll detect any attempts to communicate between Alice and Bob. So that's not good, but most channels have thermal noise in them, and what we can show is that the mean photon number constraint on Alice obeys this quantity, and this is for the relative entropy metric that Matthew has mentioned in part 2 of this tutorial. So we can use a Holow bound, entropy bound bosonic systems, as well as stereo series expansions to obtain this result. And my student Michael Bullock did that in 2020 for JSAC, who's actually here with us in this tutorial. Now, the SRL square root law communication, we characterize it up to 2nd order, and the key technical tool here without this tool, our work will be possible, is a very recent union bound for that enables finite block length capacity analysis in the setting where the number of where the Hilbert space dimensionality is infinite, which is what happens in this particular bosonic channels. They live in infinite dimensional Hilbert spaces, which is what makes many of the results not usable. So, and we can, so we have this good law that is essentially in the form that Matthew and Meredith found for part 2. What's interesting is that when you add an entangled resource, in our case, it's 2 mole vacuum state, which is very common. You can generate in the lab if you have resources to do that. The capacity goes to square root of m times log of n. So you get this additional log of n factor, which is really interesting, and which we have also characterized up to 2nd order. 2nd order goes as fourth root of n times log of n, so log of n term remains. And one thing that I will have to say is that there is a joint detection receiver on paper, not on metal, that achieves half the core capacity, and which was presented in last year's SSE. And the results for both the unentangled assisted and entangled assisted capacity for Bosonic channels are in our JSAID paper from 2020. So this concludes the tutorial. I will not go through a slide, but these are various areas that we think are worth looking at, and I want to acknowledge our colleagues as well as sponsors. So I think I made it. We have 15 minutes for questions. Sorry about the speed at which I was speaking. I hope that it was somewhat understandable. So
thank you so much, Bulat. Thank you, Matthew. So is there any question from the audiences?
I'm gonna look at the chat as well.
I think I answered all of them.
Oh, very good. Thank you.
So is there any other point that you want to add, Matthew or Bulat?
No, I mean, I think so. Bulat said it nicely. I mean, I think there are a lot of fun technical problems because it operates in a zero rate regime. And so I think that ties to a lot of fun things like the second order asymptotics that were popularized over the last decade, but also, you know, all the physical layer security. The coding is, I think, something that excites me a lot because you need some weird codes. And I think that there's a lot of stuff to do. The codes we have, even though they work, they're very inefficient in many ways. And lastly, as Bulat mentioned, there's a lot of cool stuff in the quantum world. I mean, people in the quantum world are a bit paranoid. So I think talking about these extreme security measures is something that they're receptive to. But there's a lot to be done. I mean, I think the only experiment to date is something that Bulat did, you know, prior to 2015. So a lot to be done in that space as well. But I think there's cool stuff. And we did not at all touch upon the more communication theoretic approaches, which don't worry so much about coding. I think coding is important, but they look at more system level aspects. There's a lot of exciting stuff going on. So if anyone's interested, I think we'll provide very extensive references in the final deck of slides so that people can explore.
So before we go, so there are some questions and answers in the chat box. So are you happy for these questions and answers being shared with the audiences as part of the link for the video?
Yeah, absolutely.
Sure.
And
yeah, sure.
I've downloaded everything too. And yeah, thanks to those of you who stuck until the very end. I think there are still quite a few. So thanks a lot for sticking around.
Yeah, thank you so much, everyone. So if there isn't anything else to discuss, let's thank the speakers, Bulat and Matthew, for this great talk and lots of information being conveyed, and hope everyone enjoyed it. And we will share the link and the slides, and also more information will be shared by Matthew and Bulat in next few days. Thank you, everyone. Have a great rest of the day, and hope to see you in the rest of ISIT this year. Thank you, everyone.
Thanks a lot, Mayar.
Thank you.
Thank you for respect.
Bye.